Hello friends, my name is Tushar and today I'm going to talk about how to create a suffix tree using Ukkonen's algorithm. So what is a suffix tree? A suffix tree is a tree representing all the suffixes of a string. For example, if I have a string x, y, z, x dollar, the possible suffixes of this string are x, y, z, x dollar, y, z, x dollar, z, x dollar, x dollar and then dollar. So this tree here represents all the suffixes of this string. So x, y, z, x dollar and then 0 represents the index from which this suffix starts. Then y, z, x dollar, x dollar and then dollar. There are many possible applications of suffix tree like substring search, and I have discussed them in another video. In this video we are totally going to concentrate on how to create a suffix tree using Ukkonen's algorithm, which is a linear time algorithm if the size of the character set is constant. This is a really long video, so I have divided this video into multiple sections and you can jump to other sections if you want to skip the introduction. Also, it really helps if you have done some reading on the Ukkonen's algorithm before watching this video. So next, let's start with how do we create a suffix tree using O of m cube time algorithm and convert that into O of m time algorithm. Let's try to create a suffix tree for this string here using O of m cube time algorithm. So I have I and j. I is my face and j is my extension. So when my I and j is 0, I check is there a path from root starting with x. So there is none, so we create one. So this is a rule 2 extension. If there is no path with certain label, create a leaf node. So we just created one. Then we increment our I by 1, so we start the next phase. J is again at the 0. We check is there a path with label j to I, which is x, y. So there is x but there is no y, so we add y here. So this is a rule 1 extension where we go till the end and then we add the new character at the end. So this at end of the leaf. So this is a rule 1 extension. Then I increment my j by 1, so I increase my extension. And then I check is there a path from root with y label. So there is none, so we create 1. So this is a rule 2 extension. Then my I becomes 3, so I start the third phase and extension 0. So I again check is there a path with label from j to y, x, y, z. So there is x, there is y, there is no z, so I create 1. Again by rule 1 extension. Then my j becomes 1. I check is there a path with j to I, which is yz. So there is y, there is no z. So we add it as a part of rule 1 extension. And then my j becomes 2. And we check is there a path from root with z label. So there is none. So we create 1. Z. So I start the next phase and extension again starts from 0. Is there a path with label x, y, z, x? So there is x, y, z but there is no x, so we add x. Then is there a path with label y, z, x? So there is none, so we add one y, z and then x. Is there a path with label z, x? So there is z but no x, so we add 1. And finally we check is there a path with label x? So there is a path with label x, so we stop and do nothing. So this is a rule 3 extension. If the path already exists, then do nothing. So this is a rule 3 extension. So at this point of time, my tree is an implicit suffix tree. By implicit suffix tree, I mean that all the suffixes of this string do not end in a leaf. So here, x, y, z, x, this ends in a leaf. Y, z, x ends in a leaf, z, x ends in a leaf, but just x suffix x doesn't end in a leaf. And at this point, my tree is an implicit suffix tree. If the last character of a string is unique, then the implicit suffix tree turns into a true suffix tree, which is why most of these algorithms add a dollar at the end, which is a unique character to convert an implicit suffix tree into a true suffix tree. So finally, let's start our last extension, last phase. So this is I, this is j. So is there a path with y, z, x dollar? So x, y, z, x dollar, x, y, z, x, and then we add dollar here as a rule 1 extension. Then j goes here, so we start the next extension. we go y, z, x, and then we add a dollar here. Then j goes here. So there is z, x, and then we add a dollar here. Then j goes here. So we come to x, and then instead, so the next character is not dollar. So at this point, we'll have to create an internal node here, and that will lead to dollar. So at this point, this guy has two edges. One is x, y, z, x dollar, and then the other one is x dollar. And finally, j becomes this guy. So we create a new edge with dollar. So at this point, I converted my implicit suffix tree into a true suffix tree, because now all the suffixes end in a leaf. X, y, z, x dollar, y, z, x dollar, z, x dollar, x dollar, and then dollar. It's easy to see why it is an O of m cube time algorithm. For every phase, I'm doing O of m square time work, and there are m phases, so the total algorithm time is O of m cube. We also looked at 3 rules. Rule extension. Rule 1 extension was walk till the end and then add the new character. Rule 2 extension was if there is no path, create a path. And rule 3 extension was if the path already exists, then do nothing. Let's look at these rules and tricks for Ukkonen's algorithm a little bit more to understand how the Ukkonen's algorithm works and how we can convert this O of m cube time algorithm into O of m time algorithm. Let's again understand our extension rules. So for this string, I have this suffix tree. Suppose we had more characters. So suppose there was a at the end. So our rule 1 extension says that go till the end of the path, x, y, z, x dollar, and add a at the end. So go to the end, for all the leaves, go to the end of the leaf and add this new character. So y, z, x dollar a, and then dollar a, and then x dollar a. So this is a rule 1 extension. For all the leaves, add the new character at the end, because that's what we're doing. We are walking the tree, reaching the end, realize that the a doesn't exist, so we add a at the end. Then we'll add a, because there is no path from root with a. So this is a rule 2 extension. If a path doesn't exist, add 1. Let's suppose we had x. So again, by rule 1 extension, all the leaf node automatically will get x at the end. Then from the root, for the last extension of this phase, we check from the root, is there a path with x? So there is one. So at this point we do nothing. So 0 to 5 extensions were added by having an x at the end. And for the last extension here, since we already had a path from root with x, we did nothing. So that's a rule 3 extension. Suppose there was y at the end of this. So again, everyone gets a y, all the leaves get y at the end as a part of rule 1 extension. And then we check here, for this guy here, there is x, and then there is a path from x to y as well. So we come here and we do nothing. So this is a rule 3 extension. So finally, let's suppose there is a b at the end. So all the leaves get b at the end as a part of rule 1 extension. And then we have x for this guy here. We have x, we have y, but there is no b. So we add a b here. So this is a rule 2 extension. So where if the path doesn't exist, create one. So this becomes an internal node. And there is 2 paths from here, one towards b and the other one towards this one. And then we go to, for this guy, yb, we go here and then we add b here. So there is yb, one path here and the other path is this one. As you can see from here, the path, this path and this path is exactly same. For the internal node here and the internal node here has the exact same path after this internal node. And then finally we'll add a b here. So that's a rule 2 extension. So these are the 3 rules of Ukkonen's algorithm. and we will be mostly improving on these ones so that we can convert this O of m cube time algorithm into O of m time algorithm. So let's look at those tricks one by one very quickly. Trick 1 is skip count and edge label compression. So what edge label compression means is, instead of storing the actual characters on the edge, we will store the index range of those characters in the input array. So for x, we'll store it starts from 0 and ends at 0. So instead of x, we'll store 0, 0. Instead of y, z, x dollar, we'll store 1 to 4. Instead of y, z, x dollar, again we'll store 1 to 4. 1, 2, 3, 4. Instead of zx dollar, we'll store 2 to 4. Instead of dollar, we'll store 4, 4. So by using edge level compression, it reduces our space complexity by a lot, and our runtime complexity would never get better than O of m squared if it did not use edge level compression. What is skip count? We'll look at what skip count means when we run through an example. Our trick 2 is that rule 3 extension is a showstopper. What was rule 3 extension? When a suffix already exists in a tree, that's when a rule 3 extension happens. So as soon as a rule 3 extension happens, what this trick says is that stop the current phase and start the next phase. Again, we'll look at it more in the example. Trick 3 is to have a global end for the leaves. So what that means is, on the leaves, instead of saying 1, 4, we'll say 1 end on all the leaf nodes. So this one, this one, this one, this one, and this one. So having one global end index, what happens is, if a new character comes in, so if say there was an A after this, so if I just increment my end by 1, all my rule 1 extension gets taken care of in O of 1 time. So if my end is 5, this edge is really representing y, z, x, dollar $a, since my end is 5, 1 to 5. This edge is really representing 4 to 5, so dollar $a. This edge is representing zx, dollar $a. This is representing y, zx, dollar $a, and this is representing dollar $a. So this is only applicable for the leaf nodes, not for the internal nodes. Next, let's look at the suffix link. So here I have a suffix tree for this string. So let's understand what suffix link means. For every internal node v with the path t alpha, where t is a single character while alpha is 0 or more characters, there is another internal node sv with alpha, which is the suffix link of v. If alpha is null, then the suffix link is root. Let's try to understand here. So b is a suffix link of a. So what is the path of a? X, y. Here x is t and y is alpha. So then b with the label y will be the suffix link of a as per this definition. Again, let's see. D is the suffix link of c. So what is the path of c from root? X, y, z. Here t is x. Again, t is a single character while alpha is 0 or more characters. And this is alpha. So then d must be having a path yz, yz, which is why d is the suffix link of c. As per the paper, there is a proof which says that every internal node will have a suffix link to either another internal node or to the root. Why suffix link is important? Suffix link is important because it helps us traverse between the nodes quickly, which will help us improve our run time. How do we create the suffix link? When a new internal node is created during an extension and of a phase, if there is another new internal node created during the next extension of the same phase, then that new internal node will be the suffix link of the older internal node. And we'll again look at it in the example. There are a few more things we need to go before we jump into the example. So let's finish up those things. Let's talk about active points. Active points is a point from which the next extension or the next phase will start. So there are a few rules for the active points. First rule is, if your active length is 0, it means that you are going to start the next extension or the next phase from root. So in this scenario here, our active length will be 0, so we're starting from root. So say there was an x after this. So we'll start from root. Since our active length is 0, we'll start from root and check, is there a path from root with x? And there is one, so we move in this direction. So if you recall, this is a rule 3 extension. So let's talk about active points and rule 3 extension. When a rule 3 extension happens, all you do is you increment your active length by 1. So in this case, our active length becomes 1 and your active edge becomes 0. Active edge is the index of the actual character. So basically saying from root, move in the direction of 0, which is x, and move 1 length. So let's say we had another y after this. Then we start our phase from here and check what is the next character. So the next character is y. So what we do is we move this cursor here, basically just incrementing our active length by 1. So again, our active node is root. Our active edge index is 0, which is x, so move in the direction of x, and active length is 2, so saying move 2 in the direction of x. So this is where the next phase will start. So now if we had z, then we are going to jump this internal node and come to this point. When we jump this internal node, then our active node will change. So now our active node becomes a. Our active edge becomes the index of z, which is 2, and our active length becomes 1. So these are the two rules for active points and rule 3 extension, which is if you're moving on the same edge, then just increment your active length by 1, and if you are jumping the internal node, then reset your active edge, active node, and active length accordingly. Next, let's look at active points and rule 2 extension. Let's understand active points and rule 2 extension. So let's say the next character after this was x. So since active length is 0, we check, is there a path with x starting from root? There is one, so we just move here and we reset our active edge to be 0, which is index of x, and active length to be 1, as we discussed before. And this is a rule 3 extension. Next, let's suppose the next character was y. So this comes to this point. Since the next character here is y, and we just increased our active length by 1, as we discussed for rule 3 extension. So let's say the next character after this is b. So from y, there is a path to x and there is a path to z. So there is no path to b. So we create a path to b from here. This is a rule 2 extension. Then we check, is the active node root? So the active node at this point is root. So what we do is we just decrement our active length by 1. So this becomes 1. And increment our active edge by 1. So this becomes 1 again. So then we start continuing from that point. So active node is root. Active edge is 1, which is y. And active length is 1. So we move in this direction here. So from here, we reach this point. You can see y. So we created a y, x, y, b here. So that took care of x, y, b. Now we have to take care of y, b. So y, b, suffix y, b, which is why we reach this point using our active points information for rule 2 extension. So here again, we create our new node b. This takes care of y, b. And then we again decrement our active length to 0. By 1. So as soon as active length becomes 0, what we do is we just do we check if there is a path with b from root. There is none, so we create 1. Alright, let's look at the other rule for rule 3 extension and active points. Suppose we did not have b at the end here. So suppose we just finished y. So we would be here. Our active node will be root, our active edge index will be 0, which is moving in the direction of x, and active length is 2, so move 2 in the direction of x. So we would be here. Let's suppose the next character after this was z. So what happens is, we check, is there a path z from y? There is one, so we move here. and then our active node changes as we discussed. Our active node will then become A. Our active edge will become Z, which is 2. Index of Z, which is 2, and then our active length will become 1. Now let's suppose there is a B after this. So then from Z there is no path with B, so we create a new B here by rule 2 extension. Then what we do is we check, is the active node root? So the active node is not root, it's A. So we follow the suffix link. This is where suffix link comes into the picture. We follow the suffix link, reach this point B, and from B again we go to Z and then check, is there a B after this? So there is none. So we create a path, we create a new leaf with path B, and now our active node becomes B, and we do not change active edge or active length. Then once we are done creating this new leaf with path B, we go again follow the suffix link from B, and the suffix link of B is root, so we reach here. So then our active node becomes root, and then we again move 1 in the direction of 2, which is Z, so we move here, and again here also there is no B, so we create that B. And then now that your active node is root, what you do is you decrement your active length by 1, as we discussed before. And then when you decrement your active length by 1, we check from root, is there a path for B? None, so we create 1. So you see how we created this suffix XYZB, XYZB moving from here. Then we followed the suffix link, came to this point and created, took care of suffix YZB, 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 and then we followed the suffix link, came here, come to this point, and then took care of suffix ZB, ZB, and then finally we came to the root and took care of suffix B. So this is where active point and rule 2 extension comes in the picture. So I think we have taken care of all the rules, tricks, and everything. So finally, let's look at the example. Let's apply all that knowledge into one of the examples. At this point, we are ready to get our hands dirty with an example. So here I have a string, and we are going to apply our rules and tricks of Ukkonen's algorithm and try to create a suffix tree for this string in linear time. So remaining is going to tell me how many suffixes are still needed to be remains to be created, and this we already talked about: active node, active edge, and active length. And end is used for our global end, which is our trick 3. So I start from root. My phase is I. So when a phase starts, first thing we do is we increment our remaining. So remaining becomes 1. And we also increment end. So end becomes 0. Then we go into a while loop while remaining is greater than 0. So remaining is greater than 0. So from root, since our active length is 0, we check, is there a path with x from root? So there is none, so we create 1. Remember, by our path label compression, we are really going to store the range on the edge, not the actual character. But for our convenience, we are also going to store the character here. So x. Then, since you create a leaf node, you change your remaining, so remaining becomes 0. Also, since it was a rule 2 extension, we do not touch the active node, active edge, or active length. So then, since the remaining is 0, we start the next phase. So I goes to 1. Again, first thing we do is we increase our remaining by 1. So remaining becomes 1. And end becomes 1. So as soon as this end becomes 1, our rule 1 extension gets taken care of for free, because now this edge is really representing 0 to 1, so x to y. So we did nothing, just by incrementing end by 1, this extension got taken care of. Then, since the active length is 0, we check, is there a path from root starting with y? So there is none, so we create 1. And that will be 1 comma end. And again, we're just going to store y for our convenience. Then, since we created a new leaf edge what we'll do is we'll decrement our remaining by 1, so remaining becomes 0. As soon as remaining becomes 0, we break out of the while loop and start the next phase. So then our I becomes 2. First thing we do is we increment our remaining by 1, so remaining becomes 1. Then we increment our end, so end becomes 2. So as soon as n becomes 2, our rule 1 extension gets taken care of by free. So this edge really represents x, y and z. And this edge really represents y and z. Then since the active length is 0, we check is there a path from root starting with z. So there is none. So we create 1. And it's really 2, end. Since we created a leaf edge, we'll decrement our remaining by 1. So remaining becomes 0. And since remaining is 0, we break out of the while loop and start the next phase. So I becomes 3. So again, we increment our remaining by 1 and go into this for loop while remaining is greater than 0. Also we increment our end. So end becomes 3. So as soon as n becomes 3, our rule 1 extension happens. So this really is representing x, y, z, x. And this is representing y, z, x. And this is representing z, x. So now since the active length is 0, we check is there a path from root starting with x. So there is this path. So what happens here is at this point, we change our active edge to be 0, which is the start of this edge, which is the start index of this edge, so that's 0. So active edge becomes 0, and active length, it gets incremented by 1, so that becomes 1. So what we are saying is that the next phase will start from this point. So what happened right now is, we had a rule 3 extension, and by trick 2, rule 3 extension is a showstopper, so we stop at this point, end the current phase, and start the next phase. So that also means that we don't change our remaining. So I becomes 4. So at this point, if we talked before, at this point the tree is an implicit suffix tree. It means that all the suffixes are not ending in a leaf. This x suffix is not ending in a leaf since the last character is not unique. Anyways, let's start the phase 4. So I is 4. So first thing we do is we increment our remaining by 1. So remaining becomes 2. Then we increment our end by 1, so end becomes 4. As soon as end becomes 4, this guy is really representing x, y, z, x, y. This is really representing z, x, y. This is representing y, z, x, y. Then we start our processing from our active point. How to find our active point? From active node root, go in the direction of index 0, which is x, and move active length 1. So move 1 in the direction of x. So that's where our phase will start. So from here we check, is the next character from here this character y? So the next character from here is y. So we move this by 1. Again a rule 3 extension happens, and rule 3 extension is a showstopper. So before we do that, let's increment this to 2. So rule 3 extension is a showstopper. So we do nothing, end this phase and start the next phase. So our I becomes 5. So first thing we do is we increment our remaining by 1, so remaining becomes 3. N becomes 5. So as soon as n becomes 5, this edge is really representing x, y, z, x, y, a. This is really representing z, x, y, a, and this is really representing y, z, x, y, a. Then, this is our active point, which we can derive from here. Active node is root, active edges move in the direction of x, because index of x is 0, and active length is 2. So move 2 in the direction of x. So this is where we are starting our phase, and we check from here, is the next guy from here A, which is what we are looking for. So the next guy from here is not A. So at this point, we'll have to create an internal node here, and that will have two child, one going in the direction of z, x, y, a, and another in the direction of a. So let me create that very quickly. So here I created a new internal node at this point, and this internal node has two edges. One is in the direction of a and another is in the direction of z, x, y, a. So this is representing x, y, z, x, y, a, and this path is representing x, y, and a. So again, the end for this one is 0 to 1, x to y, and the other end is as before, 2 to end, z, x, y, a, and 5 to end, which is a. So now we create an internal node. So we know that every internal node has a suffix link. So for now, I'll point this suffix link to root. If a new internal node is created in the next extension of the same phase, then I'll point this internal node to that. So since we created a leaf node, I'll decrement my remaining by 1. So remaining becomes 2. Then I have to check where is the next point I go to. So since my active node is root, we already talked about it before. What I do is I decrement my active length by 1. So active length becomes 1. And I increment my active edge by 1. So active edge also becomes 1. So at this point, we'll go to this place. So active node is root, active edge is 1. So 1 at index 1 we have y. So move in the direction of y, and active length is 1. So move 1 in the direction of y. So basically come to this point. So we created we took care of suffix x, y, a. So next we have to do is take care of suffix y, a. So is the next character from here a? So the next character from here is not a, it's z. So what we're going to do is we are going to create an internal node here and create a new leaf edge with a and the other one with z, x, y, a. So let me do that quickly. So here I created a new internal node. And now this has two edges. One goes towards a to represent this suffix, and the other one goes in direction of z, x, y, a to represent this suffix. So as I said before, if a new internal node is created, I'll change the suffix link from root to that guy. So this now points to this guy. Let's call it capital L and let's call it capital M, this internal nodes, and this is root R. So then we check, our active length is still, at this point our active length is still not 0. So next we do is, since our active node is root, we increment our active edge by 1. So active edge becomes 2, and we decrement our active length by 1, so active length becomes 0. So we know that, and also since we created a leaf edge, we decrement our remaining by 1, so remaining becomes 1. So we know that since active length is 0, we are going to check, is there a path from root starting with a? So there is a path. There is no path, so we'll have to create one. So we'll create a, and this will be 5, end. And since we created a new edge, leaf edge, we'll decrement our remaining by 1. So remaining becomes 0. So since remaining is 0, we break out of this for loop, this while loop, and end the current phase. So this is what happened. So till this point, till I was 4, it was the implicit suffix tree, and since a is a unique character, it converted this implicit suffix tree into a true suffix tree, which is what we are seeing right now. Also, I forgot to mention, this M suffix link will be root. Alright, let's start the 6th phase. So I becomes 6. So first thing we do is we increment our remaining by 1. So remaining becomes 1. We increment our end by 1. So end becomes 6. So then rule 1 extension gets taken care of. So this guy is now really representing z, x, y, a, x. This is representing AX. This is representing X. This is representing AX. This is representing X, and this is representing AX. So all the leaf nodes, rule 1 extension gets taken care of by just incrementing end by 1. Then we check, is there a path from root starting with X? So there is this path. So what happens is a rule 3 extension comes into the picture, and rule 3 is a showstopper, so we stop at that point. Also we update our active edge. Active edge becomes 0, which is this start point of this edge, and active length becomes 1. So basically the next phase will start from this point, as we already discussed before. So we end this phase, we don't change the remaining, and we start the next phase. So first thing we do is we increment our remaining by 1, so remaining becomes 2, my end becomes 7. So as soon as end is 7, this is representing Y, 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 and Y. Then we go into this while loop while remaining is greater than 2. So then I check from X, since that's my active point, is the next character from after X Y, because that's the Y I'm looking for. So the next character after X is actually Y. So again a rule 3 extension happens, and we just change our active length by 1, so it becomes 2. So again rule 3 extension is a showstopper, so we break out of this while loop and end the current phase and start the next phase. So then I becomes 8. So since I is 8 now, first thing I do is I increment my remaining by 1. So this remaining is really telling me how many suffixes still need to be created. Then we increment our end by 1, so end becomes 8. Since end is 8, this is really Z, 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 Z. Okay. So our while remaining is greater than 0, which is true. So we check, is there a next character from here? Is there a Z after this guy? Since that's the Z we are looking for. Is there a Z from here? So there is a Z from here. So what we do is, we jump this index internal node and come to this point. And we already talked about it. When we jump this internal node, we change our active node, active edge, and active length. So now my active node becomes L. And my active edge becomes the start of this edge, which is 2. And my active length becomes 1. And this is a rule 3 extension, so again it's a showstopper, so we stop at this point and start the next phase. So I becomes 9. So this is where our next phase will start from. So since I becomes 9, first thing we do is we increment our remaining by 1. So remaining becomes 4. And end becomes 9. Since end is 9, there is a dollar at the end of every leaf path. And okay, so where do we start? So again, how we know we have to start from A, from Z, because active node is L, so active node is this guy. Active edge is 2, it means move in the direction of Z. And active length is 1, it means move 1 in the direction of Z. So this is where our phase will start. So then we check, is the next character after this dollar? So the next character after this is X, it's not dollar. So what we're going to do is we're going to create a new internal node here with dollar to take care of this Z dollar. So let me do that quickly. So what I did here was I created a new internal node, and that has now 2 paths, one towards dollar and one towards the old XYA, XYZ dollar. So this path takes care of this XYZ dollar. So this takes care of XYZ dollar suffix. Next, since we created a new leaf node, first we do is decrement our remaining. So remaining becomes 3. Then we talked about if a new internal node is created, first we point it to root. And if a new internal node will be created, then we'll point it from instead of root to that guy. So then let's see where we move next. So since the active node is not root, active node is L, so what we do is we directly follow the suffix link and reach this point and make this guy the new active node. So we reach to M. Then, and we don't touch active edge or active length. Then from here, we move in the direction of 2, which is Z. So move in this direction and move 1 in this direction. So we move here. So this guy is our new active point. And from here we check, is the next character dollar? So the next character here is X. So just like here, we'll have to again create a new internal node. So let me do that quickly. So here I created a new internal node Q, and the path is, it has an outgoing edge Z dollar, and the other one is before. So this takes care of the path YZ dollar, which is this one, and the other path YZ XYA XYZ dollar takes care of this suffix. So then, as I said before, if a new internal node is created, I'll make this N point to that internal node instead of pointing to root. So the suffix link from N will go to Q. Then we follow the suffix link. So our active, so the question is next, where do we go from here? Also, since we created our leaf node, so we change our remaining, so remaining becomes 2. Then I follow, since the active node is not root, I again follow the suffix link of M. So the suffix link of M is root. So active node now becomes root. And since the active node was not root before, we do not change active edge and active length. So we go to root, then we move in a direction of 2, which is Z, and we move 1 in the direction of Z. So we reach this point. And again here we check, is the next character up here dollar? So the next character here is not dollar. So again, I'll create a new internal node here. Let me do that quickly. So here I created a new internal node S, and it has 2 edges. One is in the direction of dollar. So this Z dollar takes care of this suffix, and the other one takes care of this suffix. Also, since we created an internal node here, what we are going to do is Q's suffix will be now S. Alright. So now, where do we go from here? And also, since we created a new internal node, my remaining becomes 1. So where do we go from here? Since the remaining is still greater than 0, we are still in that while loop. So since now my active root, and since now my active node is root, what we are going to do is we decrement our active length. So active length becomes 0. And as soon as active length becomes 0, we check from root, is there a path for dollar? So there is no path for dollar from root. So we create one. And since we created a new leaf node, we decrement our remaining by 1 more. So remaining becomes 0. And since remaining becomes 0, we break out of this while loop and end our current phase, and that is the end of the string also. So this is our suffix tree for this string. Let's make sure that all the suffixes are represented in this tree. So first is XYZ, XYA, XYZ dollar. So that is XYZ, XYA, XYZ dollar. Second one is YZ, XYA, XYZ dollar. Third one is Z, XYA, XYZ dollar. Fourth is XY, A, XYZ dollar. Fifth is YA, XYZ dollar. Sixth is Z. Sixth is A, XYZ dollar. Then we have X, Y, Z dollar. And then we have Y, Z dollar. And then we have Z dollar. And then we have dollar. So as you can see, we have represented all the suffixes of this. We have represented all the suffixes of this string in this suffix tree. So the only thing remains is how do we give them the index. So we also need to know at the leaf what is the starting point of that path in this, what is the starting point of that suffix in the original string? So let's do that quickly. So for this we need to do a DFS traversal of the tree and then reach the leaf node and keep the count how much we moved and then update it here. So for example, let's do a DFS from here. So we move x, y, so we moved 2, then we moved 3, then we moved 4, 5, 6, 7, 8, 9, 10. So when we reach here, we had total 10 characters passed. So we know that this guy is 0. The index of this guy is 0. Then by 0 I mean the length of this character, the length of my string minus this, which is 0. Then as part of DFS we go here and we travel this. So 1, 2, 3, 4. So we are here. So this guy will be 10 minus 4, which is 6, which is this string XYZ $. Then using as part of same DFS traversal, we'll go here. This count is 2, 3, 4, 5, 6, 7. So this is 10 minus 7, which is 3. So that's representing this suffix. Then we have traveled everything in this path. So we take another path, so let's say Z. So this is Z $, so that is 2. So this is 10 minus 2, which is 8, which is Z $. And then this one is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 10 minus 9 is 1. So this path is 1, 2, 3, 4, 5, 6, 7, 8. So 10 minus 8 is 2, representing this suffix. And then we have covered everything on Z, so we move in the direction of $. So this is 1, so 10 minus 1 is 9. So this suffix starts from 9. This one is 1, 2, 3, 4, 5, so 10 minus 5 is 5. This one starts from 5. And let's finally quickly look at Y. So this is 1, 2, 3, 4, 5, 6. So 6 minus this is 10 is 4. So 1 starting from 4. And the other one is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 minus 9 is 1. And this one is 1, 2, 3. So 10 minus 3 is 7. So again, we won't actually count the characters. We'll just sum difference the range. So for counting the total number of characters on this one, all we do is 9 minus 5 plus 1. So that is 5. Similarly on this one, 9 minus 9 plus 1, so that's 1. So we are not going to actually count the characters, we are just going to difference the range to see how many characters are on that range. So again, the total time to construct this suffix tree was O of m. Really we took 2 of m time, where m is the size of the length of the string, to construct this suffix tree, which has an upper bound of O of m. Next, let's look at another example of how to create a suffix tree. Try to create another suffix tree for string mi, ssi, ssi $. So I'll start from root. My phase starts from 0. First thing I do is I increment my remaining, so remaining becomes 1. I increment my end, so end becomes 0. Since the active length is 0, we check is there a path from root starting with m. There is none, so we create 1. Again, we are storing m just for our convenience. Really, the path is going to store this in range. Then, since we created a leaf node, remaining becomes 0. So we break out of this while loop and start the next phase. So again, first thing we do is we increase our remaining by 1. Then we go into this while loop while remaining is greater than 0. Then we increment our end, so end becomes 1. So this is now really representing mi, since end is 1. Then since the active length is 0, we check is there a path from root with starting with I. There is none, so we create 1. And since we created a new leaf edge, this becomes 0. And since remaining is 0, we end the current phase and start the next one. Again, first thing we do is we increment our remaining, so remaining becomes 1 and becomes 2. So this becomes mis and this becomes is. Then since active length is 0, we check is there a path from root starting with s. So there is none, so we create 1. and this is 2 comma end. Then remaining becomes 0 since we created this node, leaf node, and since remaining is 0, we end the current phase and start the next one. So first thing we do is we increment our remaining, so remaining becomes 1, end becomes 3. So this is now really representing MISS, this is representing ISS, and this is representing SS. Then we check, is there a path from root starting with S? So there is this path. So a rule 3 extension happens, and rule 3 is a showstopper. So what we do is we change our active edge. Active edge will become the start of this start range of this edge, so that is 2. And active length will increment by 1, so active length will become 1. And since rule 3 is a showstopper, we do nothing, change nothing, and end the current phase and start the next one. So here we check. First thing we do is we increment our remaining, so remaining becomes 2 and end becomes 4. Now where to start this phase from? Looking at active node, which is root, move in the direction of active edge, move in the direction of 2, which is S, index of S is 2, so move in the direction of S, and active length is 1, so move 1 in the direction of S. So this is where our next phase will start. So here we check, is the next character after this I? So the next character after this is S, not I. So at this point we'll have to create a new internal node. Let me create this new internal node very quickly. So here I created a new internal node, say L, and it has path I and it has path SI. Also I forgot to add I at the end of every path because we increased end by 1, so I just added that as well. So then we created this node. So we know that every internal node has a suffix link, so first I'll do is I'll update the suffix link to point to root, and then we apply our knowledge and see, since our active node is root, what we do is we just decrement our active length by 1. So active length becomes 0. Also, since we created a new internal node, our remaining becomes 1. Now since active node is 0, since active length is 0, we check, is there a path from root starting with I? So there is a path, so we move in this direction. So our active edge will now become the start of this range, which is 1, and active length will go up by 1, so active length will become 1. So this is again a rule 3 extension, and rule 3 extension is a showstopper. So we stop at this point, end the current phase and start the next phase. So then my I becomes 5. First thing I do is I increment my remaining by 1, so remaining becomes 2, end becomes 5. As soon as end becomes 5, I get this S at the end. Then I check, is the next, so this is our active point, so then we check, is the next point after this S? It is S. So what we do is we just move 1. Again a rule 3 extension comes into the picture, so we just increment our active length by 1. So active length becomes 2, change nothing else in the active node or active edge, and we end the current phase and start the next phase. So I becomes 6, remaining becomes 3, and end becomes 6. So as soon as end is 6, this is now really S at the end here. There is an S at the end here. There is an S at the end here. There is an S at the end here. Then I check, is the next character from here, this is the next character from here S, so the next character from here is S. So again, we do nothing. Rule 3 extension happens, all we do is change our active length. So this is where the next phase will start. So again, we end the current phase, start the next phase. So first thing we do is we increment our remaining by 1, we increment our end to 7. So this is now really representing this guy, this is representing this guy, this is representing this, and this is representing this. Then we check, is the next character after here I? So the next character after here is I. So again a rule 3 extension happens, which is a showstopper. So all we do is we increment our active length. and end the current phase and start the next phase. So as you can see, at this point the tree is a implicit suffix tree, it's not a true suffix tree. Now that the last character is unique, that will convert this implicit suffix tree into a true suffix tree. So again, first thing we do is we increase our remaining by 1, so remaining becomes 5, end becomes 8. Since end is 8, we get $1 for free at the end. So now the fun will begin. So now we'll say, is the next character from here $? So the next character from here is not $1. So what we are going to do is we are going to create a new internal node here and a new edge with $. So let me do that very quickly. So here I created a new internal node M. The suffix length for now points to root, and if a new internal node is created in the next extension, we'll point it to that. First thing we do is we decrement our remaining by 1, so remaining becomes 4. Then we check where do we go from here. Since we are still in the while loop, while remaining is greater than 0, so we check where do we go from here. So what we're going to do is, since the active node is root, what we do is we increment our active edge by 1, so active edge becomes 2. And we decrement our active length by 1, so active length becomes 3. So the next point we're going to go is this active point. So from root, move in the direction of 2, which is S, move in the direction of S, and then move 3 in the direction of S. So we move S here, so that's this guy. Then the next two guys are SI, so we move here and here. So we reach this point. Since we jumped this internal node, at that point our active node will also change. So our active node will become L, our active index will become 3, active edge will become 3, because that's the first, that's the lower range of this edge, and our active length will become 2. So at this point we check, is the next guy from here $? So the next guy from here is not $. So let me add so I'll create a new internal node and add a path for $. So let me do that quickly. So here I created a new internal node Q. Also I pointed my suffix length of M to Q from M to root. And then first thing we do is we decrement our remaining, so remaining becomes 3. Then we check where do we go from here. So since remaining is still greater than 0, we have to still process 3 suffixes. So we follow since the active node is not root, we follow the suffix length and reach root. Then what we're going to do is we are going to move 2 in the direction of 3, which we are going to move 2 lengths in the direction of 3. So 3 is S. So we are going to move SI from here. So we go to S and then we go to I. So we reach this point. Again, we were SI here. So then we follow the suffix length and then we move S and then I in the direction because our original edge had SI. So we move S and then we move I and then we reach this point. Again we check, is the next character from here $? So the next character is not $, so I'm going to create another internal node here with another internal node, another edge with $. So let me do that quickly. I created an internal node, let's call S, capital S, or let's call it T. I created a new internal node with the path $. And then first thing we're going to do is change our remaining to be 2. And also now Q's suffix length will be T because it was created in the next extension. This was a new internal node created in the next extension. And then from here, our question is, where do we move? Our active node was root last time, which I did not update. So since the active node is root, what we do is we decrement our, we increment our length, we decrement our length by 1. So length becomes 1. And we increment our active edge by 1. So active edge becomes 4. So from root, we move in the direction of 4, which is I, and we move 1, so we reach this point. So this is the next point we are looking at. And again from here, is the next character $? No. So let me create a new internal node here. So I created a new internal node U here. First thing I do is I point T suffix link to U. Then I change my remaining to 1. And then, since the active node is root, what we do is we decrement our active length by 1. And as soon as active length becomes 0, all we do is we check from root, is there a path for $? No, so we create 1. And this is 8, end. And then our remaining becomes 0. And as soon as remaining becomes 0, this current phase ends and we have reached the end of the string. So a lot happened in the phase 8 and we created this entire suffix tree by the end of it. And this suffix tree is a true suffix tree. Let's verify that all our strings are taken care of. $, then $, so this is good. Also let's add the index, suffix index. So this is 0. This is $, so this is 1. Then $, so this is 2. Again, to add the suffix index, you'll have to do the traversal and keep the length, and when you reach the end, you subtract the length of this string from this length to get this index. Then you go S, then you go to S. For now we're looking at this guy. So $, so this is 3. The length here is 1 plus 2 plus 3, 4, 5, 6. So 9 minus 6 is 3. Then for this guy, $. So this is 4. Then for the guy after that, $. So this is 5. Then we have $. So this is 6. And then we have $. So this is 7. And this is 8. Just $. So this is our suffix tree with the index of all the suffixes in this tree. Again, the runtime complexity of this algorithm is O of n. Alright, so next let's look at some of the code snippets, and that will conclude our discussion on the suffix tree using Ukkonen's algorithm. Let's talk about the data structure used for suffix tree. So I have a class suffix node. Our character set is ASCII set, so basically 256 characters. So every node will have at max 256 outgoing edges. And then we talked about how we are going to store the range on the edge, not the actual characters. So start and end is used for that purpose. End is a reference, so we can use one global reference for all the leaf nodes, and every internal node will have their own end reference. Index is going to store the point from which this suffix starts in the input array, and index will be -1 if it's an internal node. And then we talked about how internal node will have a suffix link, so suffix node suffix link will be useful for that purpose. Also we talked about active point. So active point will have 3 components: active length, active node, and active edge, which we already talked previously in this video. Let's try the example xyz $. So build is the main function which gets called, which creates the suffix tree. First thing we do is we initialize root, then root index is -1 because root is an internal node, and then we initialize our active point, and this end is the global end. And then there is a for loop for starting all the phases, and when all the phases are completed, we set the index for all the suffixes using this function. So initially I is 0, so we start this phase and then we go to the start phase. First thing we do is we set the last created internal node as null. Then we say end plus, so end plus means end becomes 0. This is our global end again. And then we set remaining suffix count is plus, so remaining suffix count becomes 1. While remaining suffix count is greater than 0, it is greater than 0, we check if active length is 0. So active length is 0 at this point. So we check, is there a path starting with input I from active point? So active node at this point is root, and there is no path from root starting with x. So we go into this else condition, and then we create a path from root. We create a new suffix node, and then there's a path from root with this x going towards this suffix node, and then we set remaining count minus minus, so remaining count becomes 0, and then we go to the top of this while loop, and then since remaining count is 0, we don't go into this while loop again, and then this phase ends, and at that point we start the next phase. Let me quickly show you the select node. All select node does is checks from active node, is there a path from active node towards this input of index, and that's what and if it is there is one, it returns a suffix node, otherwise it returns null. So next let's do for I is equal to 1. So this is how my tree looks at the end of phase 0. From root there is a path for x. So for I is equal to 1, we again go to start phase. First thing we do is last created internal node is null, and then we do end plus plus, so end now becomes 1, and then remaining suffix count becomes 1. So while remaining suffix count is greater than 0, we check if the active length is 0. So active length is 0 at this point, so we again go into this if condition. Again from this if condition we check, is there a path from root starting with y? So there is no path starting from root starting with y, so we go into this else condition and create a new create a new leaf node and a path from root towards that leaf node, and then set remaining suffix count to 0, so then it doesn't go into this while loop again, and we end this phase and go back to the top of my for loop. So at the end of phase 1, this is how my suffix tree looks like, x, y, and y. And now let's start phase 2 with character z. So just like before, we go to start phase, we increment our end, we increment our remaining suffix count, so remaining becomes 1. While remaining suffix count is greater than 0, it's true. The active length is still 0, so we go into this if condition. And now from root, there is no path starting with z, so we go into this else condition, create a new leaf node and mark it as a child of root with edge z. And then we decrement our remaining count, so that becomes 0, and since remaining suffix count is not greater than 0 anymore, we end this current phase and go back into this for loop here. So at the end of phase 2, this is how my tree looks like, x, y, z, and z. So next let's start the phase 3 with character x. So again we go to start phase, again we do end plus plus, so at this point end becomes 3. Our remaining suffix count after remaining suffix count plus plus, remaining suffix counts becomes 1. Then we go into this while loop. We check, is the active length 0? At this point the active length is still 0, so we go into this if condition. We check, is there a path from root starting with x? So there is a path from root starting with x, so we just go into this if condition. We make active edge as start of that path. So basically active edge at this point becomes 0, active length at this point becomes 1, and we don't change the active node, and then we break out of this while loop. So we break out of the while loop with remaining count as 1. So at the end of phase 3, this is how my tree looks like. Look at remaining is still 1 at this point. So at this point we start the phase 4 with character y. So we go into the start phase. First thing we do is last created internal node is null, then we do end plus plus, so end becomes 4. Then we increment our remaining, so remaining becomes 2. While remaining is greater than 0, it is true. We check if the active length is 0. At this point the active length is 1, it's not 0. So we go into this else condition, and then we check, is the next character after the active point is, what is the next character after active point? So the next character after active point is y. So then we check, is that character same as input I? So in this case that character is same as input I because both of them are y. So we go into this if condition, then we check, is the last created internal node not null? So that is null, so we don't go into this if condition. This is useful for setting the suffix link. And then we walk down. By walking down, it means that we go from x to y. Let me quickly show you the code for walk down. So basically we are checking, do we jump the node? If the current character was the last character of internal node, then at that point we would have jumped. But in this case we don't go into this if condition, we just go into this else condition. So we just increment our active length at this point, so active length becomes 2, and then we come back here and then we break out of this while loop and go back into this for loop. So at this point the remaining is 2 and our active point is y. Let's start the last phase, phase 5, where the character is $. So we go into the start phase, we increment our end, so end becomes 5, we increment our remaining, so remaining becomes 3, so 3 is greater than 0, so we go into this while loop, and then our active length is not 0, so we go into this else condition. We see what is the next character after the current active point. So the current active point is y, and the next character after that is z. So z is not same as input I, which is $. So we go into this else condition. What this else condition does is, till this point, it creates a new internal node, it creates a new child leaf node, and mark the two leaves node as a child of the new internal node. Then we check if the last created internal node is not null, so it was null, so it doesn't go into that if condition. Sets the last created internal node as this newly created internal node, then point the suffix link of the newly created internal node to root for now, and if a new internal node is created in the next extension, it will point to that. And then we check where do we go from here. At this point the active node is still root, so we don't go into this if condition but go into this else condition. In the else, first thing we do is we increment our active edge. So active edge becomes 1, before it was 0, and we decrement our active length. So active length also becomes 1, and then we decrement our remaining, so remaining becomes 2. So what that means is our new active point is this y here. So this is how the tree looks like after the loop 1 of phase 5. We created a new leaf node and a new internal node. So this internal node has two child, one towards $, and one towards z, x, y, $. And then the suffix link for now is pointing to root, and then this is our new active point. So we are still in this while loop, remaining at this point is 2. Then we check is the active length is 0, active length is not 0, it's 1, so we come into this else condition, and then we check what is the next character after active point. So active point is y, as you can see, because the active node is root, active edge is 1, it means move in the direction of y, which is the index of 1, which is at index 1, and move 1 length in the direction of y, so which is why this is the active point. And we check what is the next character after active point, so that's z. So that's not same as $. So again we go into this else condition. Again this code creates one new internal node and one leaf node, and then sets two leaf nodes as a child of that internal node. And then, as you remember, we set the last internal node last time. So now this node here is last created internal node. So the suffix link of this node, instead of pointing to root, will start pointing to that newly created internal node. And then the last created internal node will become this newly created internal node, and then its suffix link will now point to root. Again we check is the active node root, so active node is still root, so we come to this else condition. We increment our active edge, so active edge becomes 2, and we decrement our active length, so active length becomes 0, and then we decrement our remaining, so remaining becomes 1, and then we go back to the top of this while loop. So after loop 2 of phase 5, this is how our tree looks like. The suffix link from here goes to here, and from the suffix link of this this newly created internal node is pointing to root. So remaining at this point is still 1, so we still continue in this while loop if active length is 0. So the active length at this point is 0, so we again go into this if condition. So then we check is there a path from active node, which is root, in the direction of $, because $, is the current character under consideration. So there is no such path, so we go into this else condition, and then we create a new edge, a new leaf node with $edge, and may mark as a child of root, and then we decrement our suffix remaining, so remaining becomes 0. So we don't go into this while condition, and then we go back to the top of this for loop, and at this point the for loop is also complete because we have reached the end of the input length. So we break out of this for loop, so the only thing at this point left is to set the index for all the suffixes. This is how our final tree looks like. The total number of leaf nodes here are 1, 2, 3, 4, 5, and 6, which is the total number of characters in our input string. So all the suffixes in the input string are now represented in this tree. So the only thing this tree needs to do is have index for all the suffixes, and that we can easily do by doing a DFS traversal and counting the total number of characters encountered till you reach the leaf node, and then subtract that number from the size of your input array. For example, for this path here, the total number of characters are 1, 2, 3, 4. So the index for this one will be 6, which is the length of our input string, minus 4, which is 2, which is correct. This suffix is starting from 2, ZXY $. So this is the suffix tree with all the index set 0, 1, 2, 3, 4, and 5. This is all I have to talk about suffix tree using Ukkonen's algorithm. The link to the code is in the description section of the video. Also, check out my Facebook page and my GitHub link at github.com mission peace interview. Also, subscribe to my YouTube channel and feel free to like this video, share this video, or comment on this video. Thanks again for taking time to watch my video.